Brought these. I printed 20 of them. It's just some information on uh, electrical symbols and switches, how they symbolize them, circuits, things like that. So go ahead and pass them around. Probably one a table would be enough. Also, I made up a little board here. It has different uh, single pole, single throw switches, and double pole, double throw switches, and how they work. You push this one, lights up, let it go, or that's a momentary switch. If you got to hold it, it's like a starter on your motorcycle. That's momentary. If you push it and it's on, that's a constant on switch. Pardon? Right. And then you got your single throw, single pole switches that are off in the middle. Throw them one way, it's one light. Off in the middle, throw them another way, it's another device. And your double pole, double throw switches work the same way, but you've got two different sets of poles that you can use in them. It's kind of hard. And then this is a typical solenoid. Solenoid is nothing but a piece of metal surrounded by a wound of copper wire that when you apply electricity to it, it'll activate. It'll be a magnet and suck whatever your switch is that you want to engage. Okay? And then I got an example of a heat shrink on here on the wire. Here's examples of some single pole, single throw switches. They come in several different styles and sizes. And some heat shrink tubes that you can pass around. See how they, before you melt it. So, okay, to begin with, when we're trying to transfer electricity, you want to do it with loosely held electrons. And the materials that have the loosely held electrons, the best one is gold. The next best is silver. And then comes copper, which is what everybody uses anymore. When we say loosely held electrons, the atoms inside a wire are bumper to bumper like this. And you got neutrons here in the middle, and your electrons are out here. And how you do that is you have electromotive force, as if in a battery. And a battery has chemicals in it that agitate the atoms, the neutrons or electrons in the atoms, forcing them out into a wire. So then you've got to replace, as these more electrons come out, this one goes on that atom, that's got to get rid of that one, goes on to the next one, that one's got to get rid of, and that creates a flow of electricity through electrons. All of this has resistance. Everything electrical has resistance. Unless you have a superconductor, which basically has no resistance, but you're talking about absolute zero to get that non-resistance. And eventually they'll have supercomputers that'll have the superconductors that'll be no resistance, and they'll be phenomenal. So let's talk about circuits. There's basically two kinds of circuits. We'll call this a battery. And electrical term for that battery is EMF, abbreviated, means electromotive force. So a common series circuit will run your battery, and then you got, say, a light, and then a light, and then a light, and then you come back to the battery. That's a series circuit. The problem is, if any one of these lights burn out, all of them are out, because you can't get a straight flow of electricity. The other circuit, which is mostly used, is a parallel circuit. Parallel circuits are designed where you have lights, say a light, and a light, and a light. And any one of these lights could burn out, and it's not going to affect the other lights in the system. Talk a little bit about AC and DC. Okay. A phase, an AC phase or a cycle looks like this on a oscilloscope. And this is 0, and this is negative, and this would be positive. And on a house circuit, this is 120 volts, and this is 120 volts. And your cycle from here to here is 60 seconds. Or you get 60 seconds in a cycle. 60 cycles in a second, 60 seconds in a cycle. So, wait a minute, that ain't right. 60 cycles in a second. Yes, per cycle. Right. You know why the United States decided to go 60 seconds in a cycle?
Well, because France did 50.
No. Clocks. Clocks work on 60 cycles. It's easier to make a clock that'll work on that rather than European in the 50s. So anyway, this would be known as an AC circuit, alternating current. Okay? Say your alternator in your bike puts out that type of phasing. So everything on a bike is DC. So in order to get DC, you take this, and what you do is you take only half of it. It's not pure DC, but it is DC. The way you do that is through a diode, usually found in your alternator, or in British terms, it's a rectifier. British call it a rectifier. What that does is it eliminates half of the alternating current and gives you DC. If you want to know anything about three-phase, like in your like industrial, three-phase is looks like this on an oscilloscope. And what that means, obviously, is you're packing in more phases in that unit, in that direction. Electrical symbols. I've passed around sheets on electrical symbols. And capacitor, we'll go by them. Resistors. If you ever look in an electronic unit in a resistor, you'll see little brown, round things like this with a wire coming out, there. They're usually colored brown, but then they'll have stripes of different colors on them. And what that is, that tells you how much resistance that particular resistor has. Like, this, say that's a white line in there and it's 2, and then another, say, brown wire or red wire, and that's 4, and then the last one will just tell you how many zeros to add. Like if this was green, maybe it'd be that many zeros. So you've got a resistance of 2,500 or 25,000 ohms. Resistance is measured in ohms. A capacitor. The capacitor is, or condenser, both the same thing. It's just a thin sheet of steel that's wrapped around in a circle several times, and it stores power and lets that power go like through like switches and points on your bike. And typically it'll store up to 20 to 30,000 volts. And that's the reason that when you get shocked off a spark plug, you can take a 12-volt battery, a human being can grab both poles and never feel a thing. Why? Because the human body has somewhere between 20,000 ohms of resistance. Some guys have it higher, some lower. I knew a guy that could work 120 volt electrical wires without even turning them off. Because he never felt it. His body resistance was higher than that. I know. So yeah. Now I got the paper's got the other symbols and so on and so forth. Right. A diode is another name for a diode is a rectifier. I think I went over that, right? Right. And transistors, the symbol for a transistor. Does anybody here work with high frequency? With high frequency, like a TIG welder or a plasma cutter or any of that? That's a a beast of its own, high frequency. I had an instructor in electronics school that also worked at a radio station, and he was a maintenance man at the radio station. And back then, when I was going to school, we were still using vacuum tubes in TVs and radios. Anyway, your radio stations had vacuum tubes as tall as men in there. I mean, these things were huge. Well, part of his duty was to take people around, groups around, and show them different things in the transmitting booth. And he carried a big screwdriver with him with a big plastic shield on the end of it and a big long screwdriver. And he'd use that as pointers. Well, one time he had some grade school kids in there, and he was pointing out different things, and he got too close to one of the vacuum tubes, and the high frequency came down the screwdriver, jumped over the shield, and nailed him. And the thing about high frequency, it travels through your bones. It'll burn little holes where it goes in and burns little holes where it goes out. But the guy said that afterwards, the kids said that all the children said he had a blue haze all around him. They thought he was the second coming of Christ. And he said he was blind for, I don't know, 3 or 4 hours. He couldn't see. He had to sit down. He couldn't see anything for about 3 or 4 hours. But I've seen high frequency travel through concrete. So it's quite scary. But
high frequency on a jig welder, if the cable gets a bunch of metal filings in it, it'll start jumping down.
right.
Yeah.
Yeah.
I worked for Fairbanks Moores, and we had 4160 there, super high voltage hitting, but we had our own power station. So one summer we hired a bunch of, you used to walk by this power station and make your hair stand up. I mean, it was serious stuff. And we hired a bunch of college kids one time, and they were looking for things to do, so they sent them out in the lot to clean up paperwork. And one of the guys, I don't know how in the hell the gate wasn't locked. I walked out there, he's inside the power station walking around picking up papers. I said, dude, just stop. I was ready to get electrocuted before he got out of there.
My old boss, he's got huge power lines that goes through his backyard. He can take a electric drill motor out in his backyard, not even plug it in, and it'll be turning. Because electrical wires have a magnetic field around them. And you get enough of that, and you can hear the power humming through the lines. Did you know why they transfer voltage rather than amperage? It's far cheaper to transfer voltage than it is amperage, because amperage the wires would have to be so huge to get enough amperage to facilitate everybody that's on that line. Where you can transfer 20,000 volts, put a transformer at a pole, and that transformer, what that does is change that 20,000 volts down to 120 or 220 volts that'll come to your house. But then you got the amperage. You reduce the voltage, you get higher amperage. And vice versa. You reduce the amperage, you get higher voltage. So that's the reason they transfer the volts rather than the amps. And amps is a measurement of electricity. Let's see here. Went through that. Parallel circuit. Okay, it's determined that the speed of electricity is also the same as the speed of light. And the speed of light, the speed of light is 186,397 miles a second. So that's moving. Huh? So that's traveling.
Yeah.
This number here, that's a light year. How many miles in a light year? So when astronomers say, you know, those planets are 100,000 light years away, they're talking about that figure times 100,000. So basically, when you're looking at stars or a moon or a sun, it's where it used to be 3 or 4 minutes past that time. Same way the further out it is. So that's quite a few miles. Rheostats and potentiometers, they're basically the same thing. Rheostat is adjustable resistor, like the volume control on your radios. That's a rheostat or potentiometer. Potentiometer is a little more involved in that, but they both do the same thing. They control the resistance. And one last thing, and if anybody wants to see it, I can demonstrate it. If you've ever done heat shrink, this is about the best source of heat shrink tool you can get. And you can really control your heat. And you can really...
I know it's mine and he keeps stealing it.
Yeah.
Use it for
Actually, yeah. No, actually, it's what's that? Cream, yeah, we bought it in a cream brulee setup, but I have seen them at Home Depot, places like that. If you go back where they have soldered guns and things like that, they will have one of these. Heat shrink. And you want to keep turning it. You don't want to apply too much heat in one spot. You can get it clear up here at the tip. And you can also do some soldering with that. So it might be a little warm. So anyway, do I have any questions? John?
What's the purpose of resistors?
Resistors to limit the flow of electrons, to force them to slow down or even eliminate some going through a unit.
So cuts the electric amount of juice that you're getting.
Amount of amperage.
Does the same thing?
What?
Diode?
Diode eliminates what a diode does. No, a diode eliminates. If you have AC, a diode eliminates the bottom half, so you have DC. That's a diode. Huh?
They both limit the supply of electricity?
No, the diode eliminates the bottom half of a sine wave. So, huh? Or the top half. It could be either half, but it'll. In order to get DC, that's AC. And in order to get DC, you have to eliminate either top or bottom of the sine wave.
So a diode just converts it from AC to DC?
Yes.
Well, it takes part of it away.
Yeah,
So
it
it
just,
leaves you to one DC.
and the thing, that's an alternator will do that. Now in a battery, you don't have to worry about that because the battery is just straight DC solid. There's no AC to it.
Okay, aren't there diodes that block electricity from backflowing?
Yes, that's what a diode does. If you look at the symbol of a diode, I think that's on the paper there. Yeah. The electrical symbol on a diode is like this. And what that means is it's one way. It'll only let the power flow one way and not the other.
So that's a different kind of diode.
Now, diode's a diode. It's going to eliminate either the top or the bottom part of a sine wave. And the only reason you'd have a sine wave on a motorcycle is you got an alternator, not a generator. Generator puts out DC. Alternator, that's the reason they call it alternator. It's alternating the electricity.
Nikola Tesla.
So-
DC.
Huh?
Tesla, because of Tesla, we got AC.
Yeah.
Yeah.
Edison and them were fighting DC, AC. I think Tesla won.
You're right. Yeah, because DC, that principle where,
They were fighting about that.
right, yet the DC, you kept losing power the farther out it went from where the power
Niagara
was
Falls
being
and
made.
Buffalo, he was going to have 19 stations. Edison. Well,
Right.
Tesla goes, I got it, all the way 20 miles to Buffalo.
Yeah,
There's a
AC.
monument, Niagara Falls or Nikola Tesla. Big monument there.
Right.
Niagara Falls.
Yes. You're right. Tesla was
Tesla's on
was the man about AC.
Like a good example of a resistor is on these old cars that use 6 volt. They don't want to burn the points up in them, so they have an inline resistor that goes to your coil in order to lower the resistance so you don't burn your points up. And that way you can deliver the full 6 volts to like a starter. They don't have a resistor in line in the starter circuit. It's just like like on the distributor and stuff. They don't want to put that voltage in there and burns up the points.
Yep. Any other questions?
Are there any superconductors?
Oh yeah, there are superconductors, and they are working on supercomputers that use a superconductor. I'm not sure what that means other than it has to be at absolute zero to be a superconductor.
Temperature-wise. Temperature?
Yeah, temperature-wise. Otherwise, everything else above that has some sort of resistance.
What kind of material?
That's what I don't know for sure. It seems to be some kind of secret, you know. So,
And they're only used in computers?
well, they're building computers that are using superconductors.
The reason they do that is because they will operate so much faster.
Right.
No resistance.
Yeah. Yeah, no resistance. That's the purpose. You know, that's why they're called superconductors. There's no resistance in them.
Yeah, but he asked, is anything else being other than computers? Would you use that in anything else?
Well, that I don't know.
Big load, quantity wise, is the cyclotrons and tracks to try to fire physics particles at each other. Many of those use superconductors, and they have to position every, for example, 100.
So they use superconductors and magnets, so it's like producing resistance because you're trying to get current loss to get.
Any other questions that I can't answer? Yes, Pat.
My son is in the Marines, he was stationed in Lorraine. He'd call me or I'd call him on the phone, and we could talk just like we're talking right now. How is that possible? I can't wrap my head around it. It's a lot of mass.
Was it done over wire or wireless?
I have no idea.
Oh. Well, yeah,
A combination.
yeah.
You gotta have fiber optics or something to go over the ocean, you know, to carry your message over satellite.
Jerry, you're a journeyman electrician, right?
He does a pretty good job.
So Jerry told me the first thing you need to do is don't let the smoke out.
You can't get back there.
Yeah.
Let the smoke out.
Yeah. When I was in electronics school, the guy told me, keep one hand in your pocket. I mean, I can take a screwdriver with my finger on it and stick it in any side of a receptacle and you won't get shocked because you're not completing the circuit. But if you did it with both, then yeah, it would nail you big time. Does anybody know why AM radio signals travel farther than FM radio signals? No. AM radio stations, the signal bounces off the atmosphere and comes back and bounces back, so it can travel back and forth off the atmosphere and the earth. FM is strictly line of sight. So, that's the reason you lose it when you go behind buildings or in a cave or whatever, because it has to be line of sight. But AM, it bounces all over and comes back to the earth, so on and so forth.
There's hardly any AM anymore.
Not anymore. But, back in the 50s and early 60s, the radio stations down in Texas and all that, you could get them all over the United States because they were broadcasting on AM.
Del Rio.
Yeah. Yeah. I mean, yeah, you had that.
The other one was WLS in Chicago.
So, anyway, I hope I didn't confuse people too much. Thank you.
I moved to TV one time. I was probably about, my parents moved and I got a TV and